Hey there and welcome. Today, we're not just learning about science, we're actually building something. We're putting together a measurement toolbox, and we're going to fill it with the essential tools that scientists all over the world use to speak a kind of shared secret language. So let's get started. So just imagine this for a second. A scientist in Japan has this huge breakthrough, and then a scientist in Brazil wants to recreate that same experiment. How do they make sure they're using the exact same amounts of everything? How do they avoid a massive mix-up? Well, that's the big problem we're going to solve today, and it all boils down to having a shared language. You see the problem right here, right? If you told someone your phone was 6 long and weighed 6, they'd have no idea what you're talking about. 6 what? Inches? Centimeters? It's just a recipe for confusion. So to fix this, we need to grab our very first tool from the toolbox. And here it is. Tool number 1 is the SI system. I want you to think of this as the universal translator for science. It's the official language that gets everybody, everywhere, on the exact same page. No more confusion. Now, the name sounds kind of fancy, doesn't it? Système International. It's just French for international system. But the idea behind it is so simple and so brilliant. Let's just create one system of measurement that all scientists agree to use. That way their work can be shared, it can be tested, and it can be understood by anyone, anywhere. It's really the foundation of our entire toolbox. So everything in this SI system starts with just a few basic building blocks. We call them base units. As you can see, for length, we use the meter. For how much stuff is in an object, that's its mass, we use the gram. For the space it takes up, its volume, we're using the liter. And for time, well, that's seconds. This simple foundation is actually incredibly powerful. Okay, quick sidebar, but this is super important. Mass and weights are absolutely not the same thing. Your mass is the amount of matter you're made of, and that number doesn't change, no matter where you go in the universe. Your weight, though, that's just the force of gravity pulling on your mass. That's why on the moon, you'd have the exact same mass, but you'd weigh a whole lot less, because the moon's gravity is way weaker. So, we've got our base units, but what if we need to measure something really, really tiny, like a single cell? Or something massive, like the distance to another galaxy? We can't use plain old meters for both. That would be ridiculous. And that's where our next trick comes in. Prefixes. You can think of these as a superpower for our SI units. Prefixes are just little tags we stick on the front of a base unit to make it bigger or smaller by a power of 10. And to remember the order, from biggest to smallest, we can use this totally silly sentence. Each first letter stands for a prefix, from giga and mega for crazy huge amounts, all the way down to milli and nano for microscopic things. It's just a handy little mnemonic to keep the order straight in your head. Okay, time for our second major tool. Knowing the units is great, but what if you're given a measurement in, say, kilometers, but you need the answer in miles? For that, we need a special method. It's called dimensional analysis, and trust me, this is a real game changer. Now, that definition sounds a little intimidating, but I promise you it's not. Dimensional analysis is just a really organized way to hop from one unit to another. The entire secret is using something called a conversion factor. You know, a simple fact, like there are 2.54 centimeters in 1 inch. We use that fact to cancel out the units we don't want and leave behind only the ones we do. All right, let's see this tool in action. Enough talk, we're going to follow these 5 simple steps to solve a real-world problem. This is how you actually use this thing, so let's just walk through it together. First things first, what are we actually trying to figure out? Well, we have a measurement in centimeters, 15 of them, and our goal is to find out what that equals in inches. Pretty straightforward. Step 2 is finding the key that unlocks the whole problem. This is our conversion factor. It's that fixed relationship between the two units. We know for a fact that 1 inch is always equal to 2.54 centimeters. This little equation is our bridge that lets us cross from the world of centimeters to the world of inches. Now, this right here is the most important part. Pay attention to how we set this up. We take our original number, 15 centimeters, and we multiply it by our conversion factor, but we write it as a fraction. And here's the secret sauce. You always, always put the unit you want to get rid of, in this case, centimeters, on the bottom of that fraction. That's the whole trick. And boom, the magic happens. Because we set it up that way, the centimeter unit on the top cancels out with the centimeter unit on the bottom. They're gone. The only unit left standing is inches, which is exactly what we wanted. Now all that's left is the math. 15 divided by 2.54 gives us our final answer, 5.91 inches. We just used our conversion tool perfectly. All right, we've got our universal language, we've got our conversion power-up. It's time for the final and maybe the most advanced tool in our toolbox. We're talking about significant figures. And this one is all about being honest and precise with our measurements. So let me ask you a quick question. Take a look at these two measurements. Are they the same thing? I mean, they look almost identical, right? But in the world of science, that extra zero on the end means everything. It tells us how good the tool was that made the measurement. 6.00 grams is a much more precise measurement than 6.0 grams. Let's dig into why that matters so much. This is hands down the best way to think about this. Imagine you're working on a project and you have two photos. One is super sharp and high def, and the other one, it's kind of blurry. If you combine them, the final image can't possibly be any sharper than your blurriest photo, right? It's the exact same with measurements. Your final calculated answer can only be as precise as your least precise or blurriest measurement. Okay, so how do we know which digits are the significant ones, the ones that count? Here are the quick and dirty rules. First, any number that isn't a zero always counts. Easy. Zeros that are sandwiched between other numbers, they always count too. Zeros at the very end, well, they only count if there's a decimal point somewhere in the number. That's why 6.00 has 3 significant figures, but a number like 500 only has 1. Okay, let's put our blurry photo rule to the test. Let's say we want to find the density of an object. We measure its mass, and our scale gives us 32 grams. That's 2 significant figures. Then we measure its volume very carefully and get 18.01 milliliters. That one has 4 significant figures. So which one is our blurry photo? It's the mass, right? It's the less precise measurement. So we do the math. Density is mass divided by volume, and we punch it into our calculator. And the calculator, of course, spits out this ridiculously long number. But hold on, we know better now, don't we? It would be totally dishonest to report that answer. Our answer can't be sharper than our blurriest photo, which only had 2 significant figures. So the very last step is to round our calculator's answer to match our least precise measurement. Since our blurry photo, the mass of 32, had 2 significant figures, our final answer must also be rounded to 2 significant figures. And that makes the correct, honest answer 1.8 grams per milliliter. See how that works? And there you have it. You've just officially filled your scientific toolbox. You've got tool number 1, the SI system, which is your universal language for clear communication. You've got tool number 2, dimensional analysis, giving you the power to convert between any units you want. And you've got tool number 3, significant figures, the precision tool to make sure you always report your results honestly. These 3 tools are the bedrock of all scientific measurement. So, I'll leave you with this thought. You now have the exact same tools that scientists all around the world rely on every single day. So, look around you. Think about your world. Now that you have the toolbox, what could you measure, what could you convert, or what could you calculate with a new level of precision and understanding? Thanks so much for joining me.